Hello physics students. Today I'm going to be talking about vertical accelerations, specifically the physics behind people taking a ride in a rocket ship or in an elevator. Before I begin with the calculations, what I'm going to do is review all the concepts behind this type of motion. So what I have here is a little demonstration to help us see the essential physics. So if I hold this spring scale at rest, in other words, it's zero acceleration, we can see that it reads approximately 10 newtons. And the reason why is because it's measuring the upward force acting on this mass over here, which is about a kilogram. And if we multiply a kilogram by 9.8, we get 9.8 newtons, or roughly, let's just say 10. So 10 newtons, if I were to draw a force diagram, I'd have 10 newtons down. That's the earth pulling down on this. And then I'd have 10 newtons up because of the spring scale pulling up. And so we have F net of 10, 10, 0. And it stays at rest, okay? Now, let me ask you a question. What would the scale read? In other words, how hard would I have to pull to make this mass go up at a constant velocity? Think about it for a second. Did you say more than 10 newtons, less than 10 newtons, or equal to 10 newtons? Well, hopefully you said going up at a constant velocity was equal to 10 newtons. And people who don't understand physics say, well, wait a minute, if it's staying at rest with 10, aren't you going to need more to lift it up? But we know our physics, and we know at rest, zero acceleration. Up at a constant velocity, zero acceleration. And from A equals F net over M, zero acceleration means F net on the other side has to be zero, still 10 and 10. So you could see that by me going up at a steady pace, and you saw this scale read 10 newtons exactly. And the same thing for moving down at a constant velocity. I could ask you, would it be more than 10, equal to 10, or less than 10 to go down at a constant velocity? And it's the same idea. Constant velocity, zero acceleration. A equals F net over M. 0 equals F net over M. F net has to be 0. So we need 10 and 10 to move down at a constant velocity. Okay? So let's jot that essential information down. Okay. So, case 1, A equals 0. The forces have to balance 10 and 10, and that means, yes, it could be at rest, or it could be moving up at a constant velocity or down at a constant velocity, as I said. So let me pause the video, give you a chance to catch up copying this down. Okay, now, the next question. What would it take to accelerate this up? Right now it's 10. To accelerate it up, go up with an increasing velocity, would it take more than 10 newtons, equal to 10 newtons, or less than 10 newtons to accelerate up? Think about it for a second. Well, hopefully you decided more than 10, because now if we want acceleration in the upward direction, we've got to have a net force in the upward direction. If we have 10 and 10, we have zero net force. So you'll see that if I let this go, this string will pull up and make it accelerate upward. And hopefully you saw the reading go up to like 11. So let's try that again. Watch carefully. You'll see it momentarily rise to 11. And then it accelerates in the upward direction. One more time.
Accelerating at 11.
Okay? With force force upward of 11, meaning a net force of 11 up, 10 down means 1 is the net force in the upward direction. We have an acceleration. So that is case 2. Okay, let me move this to the side. So acceleration upward, what we need, now notice the 10 newtons, I can't change that. That's the Earth pulling down with 10, m times 9.8. Earth pulls, doesn't matter which way I'm moving this thing. But what I can change is the upward force of, and I make it 14. Well, it could be 12 or something. It has to be greater than 10, and then it'll accelerate upward, moves up with an increasing velocity. That's one possibility. But here's another one. A lot of people don't get this. Upward acceleration is also moving down, but slowing down, okay? A lot of people don't get that. So let's say velocity moving down is negative. And if my velocity, and I want to go from negative 10, so that's how fast I'm going, and then I want to slow down. Oops. That is a positive change. So when you move down and slow down, positive acceleration. Surprising. So let me pause and give you a chance to copy this down. Okay, so I could show that moving down and slowing down, this scale reading will read more than 10. So watch this. If I launch this downward, see while it's slowing down? It goes to 11 while it's slowing down. Again, once I release it and it's slowing down, moving down, it'll read 11. 11, right? So you see that, hopefully, it's probably a little shaky, but to go down and slow down, you need more force upward, okay? I also forgot to mention, why am I calling this normal force? What I'm drawing is the force diagram of someone standing in an elevator. When you're standing in the elevator, the earth is pulling you down. What's pushing you up is the floor, so that you don't fall through it. And when there's a surface pushing so something doesn't go through it, that we call normal force. Okay, so that's the case 2. Now, case 3. How about if, so to accelerate it upward, I need more than 10 newtons. How about if I wanted this to accelerate in the downward direction? In other words, if I were to let this go, it starts going down faster and faster. Would I need more than 10 newtons, equal to 10, or less than 10? Think about it for a second. Hopefully you said less than 10. Because in order for this to go down, if the string is pulling 10 over here, and the Earth's pulling down 10, then we're at rest. But in order for it to accelerate down, I need more force in the downward direction. But I can't say, hey, planet Earth, pull down harder because I want this to go down, right? The Earth's not going to do that. The Earth's just going to keep pulling 10 newtons. So what I'm going to have to do is reduce this to less than 10. And then we will see the object accelerate down. So let me go change the weights over here. Okay, give me 1 second. All right. Okay. Uh-oh. All right, there we go. So, less than 10 newtons to let it accelerate down. Watch this. See that? As it's going down, to keep it at rest, 10. But when I let this go, the upward string will only pull 9, and the Earth still pulls down 10. So with 9 up, 10 down, we've got 1 extra down, and we've got acceleration down. So watch that again. Watch it drop to approximately 9, and then it falls downward. Oh, I fell off the pulley. And one more time. While it's accelerating down the scale, drop to 9 newtons. Okay, let's see. That'll stay. So that's the case over here. All right. When the acceleration is down, you cannot change the gravity, that's planet Earth, but you could ease up on the upward force. So if you're standing in an elevator, the floor would push up with 6, and then you go accelerate down. And that's moving down with increasing velocity as we saw here. But one thing that people often miss is that downward acceleration is also when you're going up but slowing down. Same force diagram. Let me show you. I'm going to launch this up, and then while it's slowing down, you're going to see once again, while it's moving up and slowing down, the scale reading is going to drop to like 9. So here's the launch, and you see that while it's going up, right, and slowing down, the scale reading actually dropped to like 8. All right, so one more time. Okay, so that is also downward acceleration even though you're moving up. All right, so let me now do a calculation example. So these are the concepts. Down doesn't change, but you can vary the up depending on which way you want to accelerate. So, first example. 55 kilogram student accelerates upward in an elevator at 2 meters per second squared. Determine the apparent weight. Copy that down, and then I'll explain in a second. So, oops. All right. Okay, so what do I mean by apparent weight? It turns out something you may not have realized, but when you feel your body weight, it's not actually the gravity you're feeling directly. What you're feeling is the normal force. You stand up and you feel heavy because your feet get crushed, maybe your knees get tired. That force from the floor is what you feel as your weight. If you jump out of an airplane and you're falling, you feel like there's no weight because you don't have any sensation of that as you're falling. You're freely falling. So the normal force is what you feel as the weight. Now, if you're in a bathroom, standing on a bathroom scale, and you're not moving, you're not accelerating, then if you're a 100-pound person, you stand on the scale, the earth pulls you down, the scale pushes you up with 100, the scale reading, the normal force, is your body weight. Take that same scale, jump out of an airplane, and put it under your feet, and you'll be falling, and you'll see the scale read 0. Okay, so the scale reads the normal force. Okay, so that's what we're solving for, the normal force. And what we're going to see in this case is the normal force, because we're accelerating upward, has to be greater than the gravity. So we could do first our force diagram. We could say the force of gravity shorten this up, is 55 times 9.8 is 539. But remember, you don't have to put the number on a force diagram. You need the force of gravity, though. You need that label for credit, not the numerical value. To accelerate up, as we just learned, we need more force in the upward direction. We don't know what that is. That's what we're looking for. So, to solve this, we've got to use Newton's second law. A equals F net over m. We know the acceleration is 2 meters per second squared. The F net, if you look at this diagram, it's the forward force minus the backward force. So we do this. All over the mass of 55 kilograms. So there's F net over m equals acceleration. Now all I have to do is just do a little algebra. So I'll multiply the 55 to the other side, and I get 110 equals F normal minus 539. Add 539 to both sides, and I get my F normal equaling 649 newtons. Okay? So that's the apparent weight. You feel that heavy for the moments you're accelerating. And this is a very real effect. It's not like, oh, it's an illusion, it's not real. It can have very real consequences. So let me give you an example. Let's suppose this is a person, and let's just make this easy. Let's call this 500 newtons, okay? So they normally weigh 500 newtons, but they have weak knees. And each knee is so weak because of an injury or something that if it experiences any more than 251 newtons per knee, it'll shatter, okay? So if you're standing at rest in the elevator, you got 250 newtons on one knee, 250 on the other because you're 500 newtons, and everything's okay. You hit the button for the elevator. I want to go to the top floor of the Empire State Building. I hit the button, the doors close, and then we start accelerating upward. And let's suppose the normal force, the force required is no longer 500 to stay at rest, it's 600. That's 300 per knee. But each knee shatters at 251. As soon as that elevator goes up, the knees shatter. It's as if you suddenly gained weight. So it's an apparent weight, very real consequences. In real life, if you're in a rocket ship and you accelerate too fast, your apparent weight, even for a healthy person, can become so large that you could pass out because the blood drains out of your head. So imagine a pilot of a rocket ship and then all of a sudden he passes out. Disaster, crash. So they have to keep track of these apparent weights to make sure that the pilots or the astronauts don't pass out, and you could even die if you accelerate up too fast. So something to be careful about. It's an apparent weight has real consequences. All right, let's take a look at another quick example. Okay, so we got a 55 kilogram rock climber like we had a 55 kilogram person in the elevator, but this time we're lowering them down with a rope so they're going down and accelerating. So, and this is like a speeding up acceleration. So I didn't write it out because I didn't want to get too wordy here. But so to lower somebody, again, the Earth is not going to change the force of gravity of 539 newtons. It does not change. It's always mass times 9.8 near the surface of the Earth. But this time, in order for this to go downward and accelerate, we don't need more than 539. We need less than 539. And since we're lowering them with a string, we often use a different symbol. We use T for string tension. But T, if you see it, don't panic. It's just another force. Right? Instead, it's a force that comes from a string. And then we don't usually call it F or F normal or F spring. We call it T for tension of the string. So that's all. Now, to solve for this, we once again use A equals F net over M. And now our acceleration is still 2. But now the net force, this is now the forward force, the Earth's downward 539. And this is the backwards force. So we're going to say 539 minus the tension backwards force, all over the mass of 55 kilograms. So we multiply the 55 to the other side, and we get 110 equals 539 minus T. We subtract 539 from both sides, and we're going to get negative 429 equals negative T. In other words, T equals 429 newtons. Oh, sorry. So there's how you get that solution. Let me pause, give you a chance to catch up. Okay, so again, the downward gravity doesn't change, but you can have more force in the upward direction to accelerate up or less force in the upward direction to accelerate down. One other possibility, and I won't go into it in too much detail, but sometimes maybe this is known, it's not unknown. Maybe you say this is 700 newtons is the normal force. So they could say, person elevator, the normal force is 700, or the apparent weight is 700, they're 55 kilograms, and then you determine the acceleration. See, we're solving for F in both cases. This, though, if you solve for the acceleration, I'm just going to scribble this quickly because, I don't want to get into too many details, but you would write out the equation, and then you would go, the F net is 700 newtons minus the 539 newtons, all over 55 kilograms. You'd punch that on your calculator, and you would get your answer for the acceleration. So that's today. Vertical accelerations, you always have gravity down, m times 9.8. The upward force varies, and then F net is either upward minus the gravity if you're accelerating up, or it's gravity minus the upward if you're accelerating down. Okay, so that's vertical accelerations. I hope you enjoyed the video. I'll see you in the next physics video.